That is under 2 kilonewton axial force, its elasticity and Poisson's ratio are given. We are supposed to find normal and shear strains. So this force, because it's inclined, it's going to have two effect or two component. One is horizontal component, which is going to be P times cosine 60 degree, and clearly this is our V. This is going to create a shear stress. If you calculate it, it's equal to 1 kilonewton, and it's going to have a vertical force which will produce a normal stress, and that's P. We use P to show it. It's going to be 2 times sine 60 degree, and that's going to be 1.70 around 3 kilo Newton. Now, if I find the area in which these forces are acting, I can clearly find the uh, deformation and stress, strain, all the parameters that it's asking for. Don't forget, the area that these forces are acting are it's this area. It has a 100 millimeter length and around 50 millimeter. So this is 50, this is 100, and these forces are acting on this surface. This is our V, and this is our P, which is 1.73. The procedure is pretty straightforward and identical. Sigma, the equation for sigma clearly is P over area. Don't forget, this P is the vertical component of the given 2 kilonewton. That's 173 times 10 over 3 Newton. I just write it in Newton. It's in kilonewton because Newton over millimeter square is megapascal. 50 times 100. So 50 times 100, which is 5,000. This is millimeter square, and that's going to be equal to 0.346 megapascal. This is our sigma. It remains an elastic region, therefore we can use Hooke's law to find strain, and that's equal to 0.346 megapascal divided to given elasticity, which is 4 megapascal, and that's equal to 0.087. And it's not asking for delta. If it was asking delta, then delta was going to be epsilon times this 25 millimeter. It's going to be very tiny, therefore it has not asked for it. Now let's use this V and find shear parameters. Before finding shear, I just go here and find this, use this G equation to find G based on E and given Poisson's ratio, because I don't have G yet. This is going to be 4 divided to 2 times 1 plus 0.4, and if you solve it, this is going to be 1.43 megapascal. So I have G also. Very identical equations to this one I can use to find shear strain and shear stress. So tau is V over area. It's V is 1 kilonewton, means 1 times 1000 Newton. Area, it's 5,000 because we calculated it above, and Newton over millimeter square, this is going to be megapascal, and that's equal to 0.2 megapascal. And from there gamma is tau over g. You see that the equations are very identical, very similar between shear normal and shear stress and strain. So zero point 0.2 and this is 1.43, both of them megapascal. This is going to be a unitless result.